Volumes by slicing. So far in calculus, we've been concerned with areas. Areas under curves, between curves. That's two-dimensional things. Now we're ready to look at three-dimensional things, volumes. If we wanted to know the volume of this box, we could take the area of the base, which is length times width, and we could multiply it by how high it is. If we wanted to know the volume of this cylinder, we could do a similar thing. Take the area of the base is circular, so that would be pi r squared, and multiply it by how high it is. Now, if we had something shaped like this, we could do a similar thing. We could find the area of the base, this base being a parabola for the edge here, so we could find the area under a curve here, and then we could multiply it by how high it is. So if A is the area of the base, the volume would be the area of the base multiplied by how high it is. This is great, but this only works for right solids. A right solid would be if you take a lateral edge, it's always perpendicular to the base. What if we had a solid that was not a right solid? For example, let's look at a pyramid. Well, the edge of this pyramid is not perpendicular, so it wouldn't work to do the area of the base times by how high it is, but we could look at various cross-sectional areas here as we're going up the pyramid and then multiply them by how thick they are to get a volume, and we could get an approximate for this volume of this pyramid. We could find the area of this first slab here or cross section on the bottom, and it would be the length of the side here squared, and then it would be multiplied by a little thickness. And then we could move up to this blue one and do the same thing and keep moving. You can see where we're going this. We could sum those up and have an approximate for the volume, and the more cross sections we had, the more accurate our estimate for the volume would be. And we can do this for, say, a sphere. Same kind of idea. These cross sections are discs. Pi r squared multiplied by their little thickness, and then we could sum these up. We could do more slices, get these thicknesses thinner and thinner so that we could get very close to the volume of a sphere by adding up all of these little discs. So we could have any kind of a shape like this, and we could have this idea of taking a slice and looking at a cross-sectional area then of this slice. We could find this as the area under a curve, and then we could take a little thickness. We are going to call that delta x, and we're finding that area there, and we're going to multiply it by delta x, a little thickness. And the volume of this kth slice would be this area times the thickness, and then we could sum up all of these slices to get an approximate for the volume. So we could have it look something like this. The more slices, the thinner the slices, the more accurate. We could do that even more, and if we let the number of slices go to infinity, we would have the volume of this solid. So this is the idea, and it could be any kind of a shape. And sort of notation here, we're looking on an interval. This is x sub I minus 1 and x sub I, so we're looking at a couple of x's here, just like if we had x1, x2, x3. This is just a representative interval. Then we're going to pick x sub I star, which means just an x on that interval. Find the cross-sectional area of the slice then, multiply it by the thickness of the slice, and then we could sum those up to get an approximate for our volume. So you can see where we're headed with this, because now if we let the number of slices go to infinity, so we have this sum of the volumes of each of these slices, and we let n go to infinity, this is the limit definition of the definite integral. So we could integrate from a to b and take this area at each x, multiply it by the little thickness in the limit, that becomes dx, sum all of those up, which is what the integral does, and we would have the volume. So let's look at the official definition of the volume here. We've got S, a solid that lies between x equal a and x equal b. If the cross-sectional area of S in the plane the x through x and perpendicular to the x-axis is a of x, where a is a continuous function, then the volume is the limit as n goes to infinity, summing up the volumes of each of these slices, which is the definite integral from a to b, a of x dx. So let's see this in action. We have a solid that has a base bounded by the curves y equals x squared and y equal 2 minus x squared in the xy plane, and cross sections through the solid perpendicular to the x-axis are semicircular discs. Find the volume of the solid. So we definitely want to draw a picture so we can see what's going on here. And our first curve is y equals x squared, which is just our basic parabola. And our second curve is a parabola that is reflected, so opens down, and it is shifted up 2. So this one would look something like this. So here is a rough sketch of the base of our solid. So we can see it looks like this. Now, rising up from this are these semicircular discs. So let's go ahead and see a sketch of this kind of in 3D so we can make sure we're visualizing this correctly. So you can see here is our curve 2 minus x squared, and here is our curve x squared, and here is the base. And then our solid, we have these semicircular discs, so half of a disc here. And you can see that the size of those is going to depend on where we are. Now, what is this radius? And that's going to be a function of x. So let's see here. We can see that this diameter, wherever we are along here, is going to be the difference between the two curves. It's going to be the upper curve. So if we're trying to get the radius, it's going to be 1/2 because it's half of the diameter. The upper curve, 2 minus x squared, minus the lower curve, which is x squared, and we can see that that would leave us the radius, because taking the difference between the curves would give us the diameter, and so half of that's the radius. Okay, so we could simplify that and have 1 minus x squared. So now that we have the radius of a slice, we are ready to go ahead and find the volume of this solid. Now, to go ahead and set up the integral for this volume, I need to know the limits. Well, let's go back to the picture here, and we can see what our a and b are. Well, let's compute it's where those curves intersect each other. So where x squared equals 2 minus x squared, or where 2x squared equals 2, and that means where x squared equals 1. We can see that it's going to intersect at 1 and at -1. So there's our limits of integration. And now we have the pi r squared, pi, and that's going to be 1 minus x squared squared, and then multiplied by our little thickness dx. So here is, oh, and I forgot one thing, because these are not discs, they're not complete circles, they are only half circles or semicircles, so I need a 1/2 in there. Now let's go ahead and see if we can compute this integral. So this volume is going to be, I could move the 1/2 pi out in front of the integral, so integral from -1 to 1. Let's go ahead and multiply this out. So I've got 1 minus 2x squared plus x to the 4th dx. So that's going to be 1/2 pi. This is going to be x minus 2/3 x cubed plus 1/5 x to the 5th, evaluated from -1 to 1. So our volume, I'm going to come over here to the left to compute this. We've got 1/2 pi, and evaluating this from, and actually if I'm looking at this, I can see that I have an even integral, symmetric from -1 to 1, so I could actually, be a little bit lazy and make this a little bit easier to evaluate if I went ahead and made this 0 and double this. So I'm going to do that because that'll make life a little bit easier. Then I'll have 1 minus 2/3 plus 1/5. And when we simplify that, it looks like we would get 8/15 pi. So there is the volume of our solid.